There is a smell you know, not in the way you know a perfume or a meal. Deeper than that, older than that. The particular sharp, living smell of the sea when the tide pulls back and the algae bakes in the sun. You have breathed it your whole life without ever needing a name for it. The name is dimethyl sulfide. And in April of 2025, the James Webb Space Telescope detected it in the atmosphere of a planet 124 light-years away. Not at the levels you find at a beach on a warm afternoon. At concentrations 10,000 times higher than anything measured in Earth's oceans. Rising from a world orbiting a red star so faint you cannot see it without a telescope. A world our solar system has no equivalent of. A world that, by every chemical signal we can measure from here, smells of life. For 2 years, the scientists who found it tried to make it disappear. They could not. Tonight, we go inside the most contested and consequential detection in the history of astronomy, the signal, the planet, the doubt, and the question that has been waiting beneath every civilization that has ever looked up at the night sky. We will trace how humanity learned to read the chemistry of worlds it cannot visit, examine the two completely different explanations for what that signal means, and stand at the threshold where the oldest question our species has ever asked may finally have an answer. If these are the kinds of nights you want more of, please like and subscribe. It helps us keep making them. The data is in. The debate is live. Let us begin. Somewhere in Cambridge, England, there is an office that does not look like the site of what may be the most important scientific question of the century. It looks like any other academic office. Books, a desk, a computer screen. The faint sounds of a university going about its business on the other side of a window. And on the 24th of April, 2025, that screen displayed a result that a man named Niku Madhusudan had been working toward for years, had been dreading, had been hoping for, and had been spending the previous months trying to disprove. The result had not disappeared. Madhusudan is an astrophysicist. He thinks about the atmospheres of planets he will never visit, around stars too faint to see with the naked eye, at distances so vast that the light he studies left its source before the first human civilization put words to stone. He has spent his career building the mathematical tools to read that light, to extract, from an almost impossibly faint signal, the chemical story of a world he can only ever know through a spectrum. 2 years earlier, the James Webb Space Telescope had handed his team something extraordinary. A detection in the atmosphere of a planet 124 light-years away. A molecule, a specific, unusual, biologically loaded molecule. And the signal was strong enough to publish. But one detection is never enough, not for something like this. So the team submitted for a second observation window. They waited for the planet to cross its star again. And when the new data arrived, collected this time by a completely different instrument, looking through a completely different range of wavelengths, with zero overlap with the first observation, they did not sit down hoping the signal would still be there. They sat down trying to destroy it. They tested every calibration assumption. They built alternative models. They searched for every possible explanation that did not require what the signal appeared to be saying. They ran the analysis and reran it. For months, they attempted to find the flaw that would let them set it aside as an artifact and move on. They could not find it. When Madhusudan spoke about that moment later, he described it as a shock to the system. He said it takes a while to recover from the enormity of it. These are not the words of a scientist prone to drama. These are the careful, considered words of someone for whom understatement is a professional discipline, and they carry precisely that weight. The molecule his team detected is dimethyl sulfide. You have already met it, whether you knew it or not, because the smell in the hook was not a metaphor. That specific living smell of a coastal beach, the sharp salt edge that fills your lungs when the tide retreats, and the kelp and the algae are baking in the summer heat. That is dimethyl sulfide. It is produced almost exclusively on Earth by marine phytoplankton, microscopic organisms living in the uppermost layers of the ocean. Billions upon billions of them exhaling this compound as a byproduct of breaking down a chemical they use to manage their internal chemistry. Algae blooms produce it. Kelp forests release it. Every tidal flat that has ever smelled of the sea has smelled of the work of living things. On Earth, nothing abiotic, nothing without life, produces dimethyl sulfide at atmospheric scale, which is why its detection, at concentrations roughly 10,000 times higher than anything found in Earth's marine atmosphere, rising from a planet orbiting a dim red star in the constellation Leo, is the reason we are here tonight. But before you allow that image to carry you further than the evidence currently supports, and it is an image worth sitting with, there is something important to hold alongside it. This is not a confirmed discovery. The signal is real. The data exists. Two independent instruments on the most powerful space telescope ever constructed have both detected it. But the threshold that science requires before declaring a discovery of this magnitude has not been crossed. The case is contested. There are serious scientists with serious models who believe the signal has an entirely different explanation, one that requires no life, no ocean, no biology of any kind. Tonight, we are going to hold both of those things at the same time: the wonder and the rigor, the signal and the doubt. Because one without the other is not science. It is either wishful thinking or willful dismissal, and neither of those will get us to the truth. There is a planet 124 light years away that may be the most important object humanity has ever identified. To understand what the signal means, and what it might not mean, you first need to understand what that planet actually is. Because K2-18b is not simply a distant world where life might exist. It is one of the strangest objects ever catalogued, a class of planets so unlike anything in our solar system that even describing it requires you to abandon almost every intuition you carry about what a planet is supposed to be. Here is the number that starts the story: 8.6. 8.6 times the mass of Earth, 2.6 times its radius, an orbital period of 33 days, a distance of 124 light years in the direction of the constellation Leo. These are K2-18b's vital statistics, and read as a list, they tell you very little. But sit with that mass for a moment: 8.6 times Earth, because what it implies about the kind of world this is has taken planetary scientists years to fully reckon with. Your solar system contains two categories of planet: rocky worlds, Mercury, Venus, Earth, Mars, small, dense, geologically diverse, with surfaces you could theoretically stand on, and gas giants, Jupiter, Saturn, Uranus, Neptune, enormous, gaseous, with no solid surface at all, their interiors transitioning from thick atmosphere into liquid and eventually into exotic compressed states of matter under pressures that have no equivalent on Earth's surface. K2-18b is neither of these things. It sits in a category that simply does not exist within your own cosmic neighborhood. A sub-Neptune, a world too massive to be purely rocky, too small and too low in density to be a true gas giant. Something in between. Something our solar system never made, and therefore something we have never been able to study up close. And here is what the Kepler Space Telescope revealed when it spent nearly a decade cataloguing thousands of planets across our galaxy. This category we have no local example of, this class of world our solar system omitted entirely, is the most statistically common type of planet in the Milky Way. Sub-Neptunes dominate the planetary census. They are everywhere the telescope looked. We spent decades assuming our solar system was a reasonable template for what planets tend to look like, and Kepler told us, with the quiet authority of raw data, that we were wrong. Benjamin Fulton and his colleagues formalized something important within that census in 2017. When you plot the radius distribution of small planets, all the planets Kepler found between roughly 1 and 4 times Earth's radius, a gap appears, a statistical valley. There are abundant planets below about 1.5 Earth radii, and abundant planets above about 2 Earth radii, and between those two populations, the numbers thin dramatically. The gap is not random. It reflects a physical process, likely the stripping of atmospheric envelopes by stellar radiation in the early life of planetary systems, leaving behind two distinct populations: bare rocky worlds that lost their gas, and worlds that retained it. K218b sits above the gap, comfortably above it. At 2.6 times Earth's radius, it is almost certainly a world that has held onto a substantial volatile envelope. A thick atmosphere, probably dominated by hydrogen and helium, pressing down on whatever lies beneath. Not a bare rock, something fundamentally, structurally different. Think about what that means for the question we are asking. We are not looking at an Earth-like world where the surface conditions might be vaguely familiar. We are looking at a class of planet we have never visited, never orbited, never sampled, never touched. And we are trying to determine, from 124 light-years away, whether something inside it is alive. That is the scale of the ambition here. There is one more feature of K218b's orbital mechanics that shapes everything about its character, and it is worth understanding now before the science grows more complex. The planet's orbit around its host star is not perfectly circular. It is slightly elliptical, which means over the course of each 33-day year, each complete trip around its star, the planet swings closer to the star and then pulls back to a greater distance. The variation in the amount of stellar energy the planet receives between the close approach and the far point is roughly 43%. 43%. Think about what that means for a world. On Earth, the difference in received solar energy between summer and winter drives seasons, shifts oceanic circulation patterns, and governs the annual rhythms of every ecosystem from the tropics to the poles. That variation is driven by the tilt of Earth's axis. Our distance from the Sun changes only marginally across the year. K218b's variation is not marginal. It is almost half the total energy budget, cycling through in 33 days rather than 365. Whatever exists on or in that world, ocean, atmosphere, chemistry, life, it must cope with this compressed, amplified rhythm every single month. The planet is strange. It was always going to be strange. The universe had billions of years to make it, and it made something we had never seen before. The question is not whether it is unusual. Everything about it is unusual. The question is whether unusual, in this particular case, also means alive. To begin answering that, you need to understand how a telescope 1 million miles from Earth can detect a specific molecule in the atmosphere of a planet that light takes over a century to reach. You need to understand the technique that made this detection possible. A method so elegant and so physically delicate that it borders on the miraculous, and so dependent on the specific capabilities of a single instrument that without it, none of this conversation would be happening. That instrument is the James Webb Space Telescope, and the method it uses is called transmission spectroscopy. Every time K218b crosses the face of its star, which it does every 33 days, reliably, mechanically, indifferent to whether anyone is watching, something remarkable happens to the light. Most of it is simply blocked. The planet is a dark disk moving across a brighter one, and for the duration of the crossing, the total brightness of the star as we measure it from here drops by roughly 1%. That in itself is detectable, and it is how the planet was first discovered. A dimming, a transit, a shadow crossing a star 124 light-years away, recorded by a telescope and noted in a catalogue. But there is a second, far subtler effect happening at the edges of that shadow. At the very rim where the planet's solid body meets the surrounding space, the planet is not entirely opaque. There is atmosphere there, a thin, curved shell of gas extending outward from the planet's surface, growing less dense the higher it reaches, until it fades into the vacuum of space. And during the transit, starlight does not simply stop at the planet's edge. Some of it grazes through that atmospheric shell. It enters at one limb, travels through hundreds of kilometers of alien air, and exits at the other side, changed. Changed because every molecule in the universe absorbs light at specific wavelengths. This is not a convenience of physics. It is a fundamental property of how matter and electromagnetic radiation interact. Each molecule, by virtue of its particular arrangement of atoms, absorbs photons at frequencies that correspond to its unique internal energy transitions. Water absorbs at certain wavelengths. Carbon dioxide absorbs at others. Methane has its own pattern. Dimethyl sulfide has its own pattern. These absorption features are not similar to one another. They are specific and distinctive, like fingerprints, like barcodes. No two molecules absorb in exactly the same way across the same range of wavelengths. When starlight passes through K218b's atmosphere, the molecules it encounters leave their mark on it. They remove photons at the wavelengths they absorb. When that light then reaches your telescope, you can spread it into its component wavelengths. This is what a spectrograph does, and read the gaps. The missing wavelengths tell you which molecules were present. Their depth tells you how much. You can, in effect, extract a chemical inventory of an atmosphere you will never enter, from a planet you will never approach. At a distance your mind is simply not equipped to feel. This technique is called transmission spectroscopy, and it is the reason the detection at K2-18b was possible at all. Here is the thing that should stop you for a moment though. The signal you are extracting through this method is almost incomprehensibly faint. The total dimming of the star during a K2-18b transit is about 1%. The additional dimming caused by the molecules in the atmosphere, the chemical signal buried inside that already tiny effect, is a fraction of 1%. You are trying to measure a whisper inside a quiet room from a kilometer away. The precision required is extraordinary. The margin for error is vanishingly small, and any instrument capable of achieving it must be stable, cold, and completely shielded from the thermal noise that would otherwise swamp the signal entirely. That is the engineering problem the James Webb Space Telescope was built to solve. Not specifically for this, but it solves it nonetheless. The road to transmission spectroscopy on K2-18b began well before JWST. In 2002, David Charbonneau and his colleagues used the Hubble Space Telescope to detect sodium in the atmosphere of a planet called HD 209458b, a hot Jupiter orbiting very close to its star, 8 times closer to its host than Mercury is to our Sun. It was the first time any molecule had been detected in an exoplanet atmosphere, and it proved the technique worked. Over the following 2 decades, Hubble and later ground-based instruments built out the catalogue: water vapor, carbon dioxide, methane, sodium, potassium, molecular detections becoming progressively more sophisticated as instruments improved. In 2019, Bjorn Benneker and his team pointed Hubble at K2-18b specifically and detected water vapor in its atmosphere. This was the first time water had been found at a habitable zone sub-Neptune, the first time this class of planet had revealed even a fragment of its atmospheric chemistry. The result told researchers that K2-18b's atmosphere was accessible to spectroscopy, that the signal was strong enough to detect with existing tools, and that a more capable instrument would return far richer results. That more capable instrument was already being built. The James Webb Space Telescope launched on the 25th of December 2021 from the Guiana Space Center on the northeastern coast of South America. It folded itself into the Ariane 5 rocket like a piece of mechanical origami, its 18-segment primary mirror hinged flat, its sunshield packed into a narrow tube, its instrument bay sealed against the vibrations of launch. And over the following month, as it traveled toward its destination, it unfolded. The primary mirror is 6.5 meters across, a hexagonal array of 18 individual segments, each one machined from beryllium and coated with a layer of gold, roughly 100 nanometers thick. Gold, because gold reflects infrared light efficiently and does not tarnish in the vacuum of space. Beryllium, because it is extraordinarily stiff relative to its weight, allowing the segments to hold their precise alignment under the thermal extremes of the space environment. The total surface is roughly 6 times the light-collecting area of Hubble's mirror. When all 18 segments are aligned, a process of extraordinary delicacy, achieved through hundreds of small actuators that adjust each segment to within a fraction of the wavelength of light. They behave as a single, continuous optical surface. The telescope did not enter Earth orbit. It continued past, out to a gravitational equilibrium point, called the second Lagrange point, 1 million miles from Earth in the direction directly away from the Sun. At this location, the gravitational pulls of the Earth and the Sun combine in a way that allows an object to orbit the Sun in sync with the Earth, maintaining a fixed position relative to our planet. And crucially, at this distance, the Earth, Moon, and Sun can all be placed behind the telescope simultaneously, blocked by a sun shield the size of a tennis court, made from 5 layers of a material called capton, each layer thinner than a human hair. The sun shield is why the telescope can do what it does. Infrared astronomy is the detection of heat radiation. The molecules in K218b's atmosphere absorb and emit in the infrared. And so does everything warm. Every warm object in the universe radiates infrared light. The Sun, the Earth, the Moon, the telescope's own structure and electronics. If the telescope is not kept cold, its own thermal emission drowns out the signal it is trying to detect. The sun shield reduces the temperature on the instrument side of the telescope to around -230 degrees Celsius, just 40 degrees above absolute zero. At that temperature, the telescope's own thermal noise drops to a level where the faint infrared signatures of molecules in distant atmospheres can actually be heard. 2 instrument packages aboard JWST have now been aimed at K218b. The first, used in the 2023 observation, comprised the near-infrared spectrograph and the near-infrared imager and slitless spectrograph. Instruments that operate across wavelengths from roughly 0.8 microns to 5 microns. These are the wavelengths where carbon dioxide, methane, and the initial dimethyl sulfide feature were detected. The second, used in 2025, was the mid-infrared instrument, MIRI, operating from 6 to 12 microns, a completely separate detector technology, a completely separate wavelength regime with no overlap whatsoever with the first observation. Think carefully about what it means that both return the same signal. Imagine trying to verify whether a particular gas is present in a sealed room. You send in one expert with one type of detection equipment. They report a positive result. Then you seal that expert outside, clear the room, and send in a second expert using entirely different equipment that operates on different physical principles. They also report a positive result. Neither expert's method could have produced a false positive in the same way, because the methods share no common technical assumptions. The only way both can agree is if the thing they are looking for is actually there. That is the logical structure of the K2-18b2 instrument confirmation. It does not prove the signal is biological, but it does make the case that the signal is real. That dimethyl sulfide, or something with a very similar spectral fingerprint, is genuinely present in that atmosphere, substantially harder to dismiss than a single detection would be. And yet the telescope, remarkable as it is operating at its limits here. JWST was not designed to hunt biosignatures on sub-Neptune exoplanets. This application was not in the original science brief when the telescope was conceived in the 1990s. The exoplanet science it now performs, routinely, transformatively, is the result of the field moving faster than anyone anticipated and the telescope being capable enough to keep up. But keeping up is not the same as being purpose-built. The signal-to-noise ratio for molecules in K218b's atmosphere is close to the instrument's noise floor. Small decisions about how to process the raw data, small choices about which atmospheric models to apply, can shift the apparent strength of a molecular detection in ways that matter enormously for a claim of this magnitude. That is not a criticism of the telescope. It is the reality of what it means to push any instrument to the frontier of what it was designed to do. And this is where the story stops being about an instrument and starts being about a theory. Because the signal JWST found in K2-18b's atmosphere was not a surprise to everyone. There was one scientist who had, 4 years earlier, sat down with a blank page and a set of physical equations and predicted it would be there. In 2021, Niku Madhusudan published a paper. It did not describe a discovery. It described a possibility, a class of world that had never been formally examined through the lens of habitability, a set of physical conditions that planetary science had largely ignored, and a specific, testable prediction about what a telescope might one day find if the possibility turned out to be real. The paper introduced a term, Hycean, hydrogen plus ocean, a compound word for a compound idea. The concept at its core is this: between the rocky terrestrial worlds at the small end of the planetary size distribution and the gas giants at the large end, there exists an enormous population of sub-Neptune planets, worlds with masses between roughly 1 and 10 times Earth's, enveloped in thick atmospheres of hydrogen and helium. These worlds are common. They may be the most common planets in the galaxy, and they had been dismissed, almost universally, as uninhabitable. Too large, too gaseous, too alien in their physical conditions for liquid water to persist, and therefore too inhospitable for life as we know it to gain a foothold. Madhusudan and his collaborators looked at that dismissal and asked a more careful question. Not whether Hycean worlds seemed hospitable by the standards of Earth, but whether the physics actually ruled out habitability, whether liquid water could exist beneath a hydrogen atmosphere, and if so, under what range of conditions. The answer was more interesting than the consensus had assumed. Hydrogen is not an efficient greenhouse gas in the way carbon dioxide is. Molecule for molecule, it does not trap heat as aggressively. But when you have an atmosphere massive enough that its sheer weight creates substantial pressure at the surface beneath it, even a modestly efficient greenhouse effect accumulates into significant warming. The pressure alone, pressing down on whatever liquid or solid lies beneath, raises the boiling point of water dramatically. Water that would vaporize instantly at Earth's surface pressure can remain liquid at temperatures well above 100 degrees Celsius if the pressure bearing down on it is high enough. This means a Hycean world could maintain a global liquid water ocean at stellar distances and under stellar radiation conditions, where a rocky world with a thin atmosphere like Earth's would freeze or boil. The habitable zone, as conventionally defined for rocky planets, does not apply in the same way. The physics of a thick hydrogen envelope shifts the calculation. Here is where the paper made its most consequential move. Madhusudan's team did not stop at showing that Hycean worlds could be habitable. They asked what a living Hycean ocean would look like from the outside, what atmospheric signature it would produce, and whether that signature would be detectable. The key molecule in their analysis was dimethyl sulfide. In a hydrogen atmosphere, dimethyl sulfide behaves differently than it does in Earth's oxygen-rich air. On Earth, ultraviolet radiation breaks dimethyl sulfide apart within a matter of days. The molecule is continuously produced by marine life at the ocean surface and continuously destroyed by photochemistry in the atmosphere above. The concentration at any given moment reflects a balance between biological production and atmospheric destruction. In a hydrogen atmosphere, that destruction is far slower. Hydrogen does not facilitate the photochemical reactions that tear dimethyl sulfide apart at the rate that oxygen does. The molecule persists. It accumulates. A biological source that would maintain only trace concentrations in an Earth-like atmosphere could, in the hydrogen sky of a Hycean world, build up to concentrations many times higher, concentrations that a sufficiently sensitive telescope could detect across interstellar distances. The paper made this explicit. If life exists in a Hycean ocean, dimethyl sulfide will accumulate in the hydrogen atmosphere to concentrations detectable by the James Webb Space Telescope. 4 years later, JWST detected dimethyl sulfide at K2-18b. Hold the weight of that sequence for a moment. This was not a case of finding a signal and then constructing a theory to explain it after the fact, the most natural and most dangerous trap in observational science. The theory came first. The prediction was specific, published, and peer-reviewed. Then the observation arrived and matched it. In the hierarchy of scientific evidence, a confirmed prior prediction carries far more weight than a retrospective explanation, because a prior prediction cannot be tuned to fit data that does not yet exist. That is not a minor procedural detail. It is one of the most important distinctions in evaluating competing scientific claims. Madhusudan's framework also identified K2-18b as one of the most promising Hycean candidates before the JWST observations began. The planet's mass, its radius, its atmospheric hydrogen signature, its position within the habitable zone of its star. All of these properties placed it squarely within the parameter space the Hycean model identified as viable. It was not a random target. It was a predicted target. The broader implications of the Hycean concept extend well beyond K2-18b. The class potentially includes dozens of sub-Neptunes identified in Kepler and TESS survey data, planets meeting the same basic criteria of hydrogen-rich atmospheres, appropriate mass ranges, and habitable zone orbits. K2-18b is the most studied of these, the one JWST has pointed at twice, the one where the question has become most acute. But it is not the only candidate. If the Hycean hypothesis is correct, and if K2-18b's signal is eventually confirmed, the implications do not apply to one world. They apply to a category of world that may be the most prevalent type of potentially habitable environment in the galaxy. It is a large claim. It rests on a real prediction. And it is now entangled with real data that refuses to go away. But entangled with that data is a planet. And to understand whether life there is genuinely possible, you need to understand the star it orbits. Because K2-18 is not a star like our Sun. It is something older, dimmer, and considerably more dangerous. Look up at the night sky on a clear night, away from city light, and try to count what you can see. On an excellent night, from an excellent location, you might reach 2,000 or 3,000 individual stars with the naked eye. Every one of them is a neighbor, cosmically speaking, most within a few thousand light years of Earth, all within our own galaxy. What you cannot see, because they are simply too faint, are the stars that make up the overwhelming majority of the Milky Way, red dwarfs. These are M-type stars, the smallest, dimmest, coolest stars that still fuse hydrogen in their cores and qualify, by that measure, as proper stars. Their masses range from roughly 8% to about 60% of the Sun's. Their surface temperatures hover below 3,500 Kelvin compared to the Sun's 5,778. They burn so faintly that even the nearest red dwarf to our solar system, Proxima Centauri, at just over 4 light-years away, is invisible to the unaided eye. There are roughly 400 billion stars in the Milky Way. Approximately 70 to 75% of them are red dwarfs. The universe's stellar population is dominated by objects most people have never seen, and most textbooks, until recently, largely ignored. K2-18 is one of them. It is located in the constellation Leo, 124 light-years away. It has a mass roughly 35% of the Sun's, and a luminosity so low that K2-18b, orbiting at just 13 million miles, less than a third of Mercury's distance from our own Sun, receives only about the same energy that Earth receives at 93 million miles from a far brighter star. The habitable zone mathematics work out because the star is so dim. Distance and luminosity balance each other. But that proximity to a red dwarf is not the comfortable arrangement it might appear. In their youth, their first few 100 million years, red dwarfs are extraordinarily violent. They produce stellar flares with a frequency and intensity that dwarfs anything our own Sun routinely generates. These are not the occasional, modest eruptions that Earth's magnetic field deflects with relative ease. These are surges of X-ray and ultraviolet radiation that can be thousands of times more energetic than the largest solar flares on record, occurring not once or twice a decade, but daily, sometimes multiple times a day, for hundreds of millions of years. Kevin France and his colleagues at the University of Colorado Boulder spent years measuring this radiation environment systematically. surveying nearby M-dwarf stars across ultraviolet and X-ray wavelengths through a program called the Mussels Treasury Survey. What they found confirmed the theoretical expectation in detail. Red dwarfs are hostile in ways that Sun-like stars simply are not, particularly for planets orbiting close enough to receive habitable levels of warmth. A planet at K2-18b's distance from K2-18 is bombarded with UV and X-ray radiation at rates that would, on a world without protection, sterilize any surface and shred complex molecules in the upper atmosphere on timescales far shorter than those required for life to emerge. K2-18 itself is estimated to be approximately 2.4 billion years old. For a red dwarf, that is not old. The most ancient red dwarfs still burning today have been burning since the universe was less than 1 billion years old and will continue to burn for trillions of years more, far longer than the current age of the universe. By comparison, a red dwarf at 2.4 billion years is in early middle age, and while it has settled from the peak violence of its youth, it still flares regularly and still delivers radiation pulses that Earth's sun, at the same age and with comparable activity, simply does not match in intensity. And yet, here is the paradox that defines the red dwarf as a research target. The very properties that make these stars dangerous are also what make them scientifically invaluable for the search for life. Because their habitable zones are so close, planets there transit frequently. K2-18b crosses its star every 33 days. Because the star is small, a transiting planet blocks a larger fraction of its light, making the dimming signal easier to detect. Because the star is dim, the contrast between planet and star in transmission spectroscopy is more favorable, making atmospheric molecules easier to pick out against the stellar background. Red dwarf planets are the most observationally accessible, potentially habitable worlds in the galaxy. You cannot separate the threat from the opportunity. They are the same object, viewed from different angles. The other consequence of K2-18b's orbital proximity is almost certainly tidal locking, and understanding it changes how you picture the world. Tidal locking is the process by which gravitational forces, acting over geological timescales, drain away a planet's rotation until it no longer turns relative to its host star. The Moon is tidally locked to Earth. It completes one rotation for every orbit, which is why it always shows us the same face. At 13 million miles from K2-18, K2-18b has almost certainly undergone the same process, and over a far shorter timescale than the Moon required. The result is a world divided. One hemisphere faces the star permanently. The red-orange light of K2-18 falls on it without pause, without the relief of night, without the modulation of a day-night cycle. The atmosphere on this side heats, expands, and flows. The other hemisphere faces away permanently, locked in a darkness that has never once been interrupted by its star's light. Temperatures plunging to conditions that would freeze even carbon dioxide out of the air on a world with the wrong composition. Between these two extremes lies the Terminator, the ring of perpetual dusk circling the planet where dayside meets nightside, where the star sits permanently at the horizon, casting long shadows that have not moved in billions of years. This strip is where temperatures are most moderate, where neither the full intensity of the day side nor the deep freeze of the night side fully prevails. If life exists anywhere on the surface or in the upper layers of the ocean of K2-18b, the Terminator region is where the conditions for it are least hostile. The atmospheric dynamics this creates are violent. Heat on the day side causes the hydrogen air to expand and rise, flowing at high altitude toward the night side where it cools, contracts, and descends, then flows back along the surface. The planet is wrapped in a circulation system driven entirely by the permanent temperature differential between its two faces, generating wind speeds along the Terminator that could reach hundreds of miles per hour, not seasonally, constantly, for as long as the star continues to shine. This is K2-18b's sky, a sky that never changes direction, a horizon where the star never rises and never sets, a hydrogen wind that has been blowing in the same direction since before complex life appeared on Earth. Now go deeper. Below that sky, in the Hycean model, is where the story of K218b becomes both beautiful and strange in equal measure. The interior of a world at this mass and density is layered like a compressed archive of planetary science. At the center, a rocky core, not Earth's basaltic and granitic rock, but rock under pressures millions of times greater than anything at Earth's surface, compressed into mineralogical phases that do not exist in any natural formation accessible to us. Above that, a layer of water ice, not the crystalline hexagonal structure of the ice in a glass, but water molecules locked into the denser configurations known as Ice 7 and Ice 10, phases that form only under the kinds of pressure that the interior of a massive sub-Neptune generates continuously. This ice does not melt easily. Under the conditions deep inside K218b, water in solid form can persist at temperatures far above what you would consider hot. And above that ice layer, in the Hycean model, is an ocean, not a sea. An ocean in the most total sense of the word, global, unbroken, stretching from horizon to horizon, across an entire planet, with no continent anywhere, no island, no reef, no shallow zone grading into land, just water, deep and undivided, pressing upward against the base of the hydrogen atmosphere above it. The conditions at the surface of this ocean are unlike anything in Earth's maritime environment. Pressure at the water surface may be 10 to 100 times greater than sea level atmospheric pressure on Earth. At that pressure, water does not boil at 100 degrees Celsius. The boiling point rises with pressure, and under enough of it, liquid water can persist at temperatures that would feel like an industrial furnace. The upper layer of the ocean could be hot by any human standard, and still be liquid water, still be a medium in which chemistry, and perhaps biology, could operate. This is what the Hycean model proposes is beneath the signal, not a surface, not rock or lava or frozen ground. A planet-wide body of hot, pressurized water, capped by a sky of hydrogen, bathed in the radiation of a red star, orbiting in a rhythm of 33 days that has been repeating without interruption for over 2 billion years. Whether life has found a way to exist in that ocean is the question. Whether there is an ocean there at all is also, as it happens, a question, and a contested one. Because the model that competes with the Hycean hypothesis does not see water when it looks at K218b's interior. It sees something else entirely, something hotter, something that changes the meaning of every molecule the telescope has detected. But before we examine what that competing model proposes, you need to understand what the signal itself actually is, and why the scientists who found it have spent 2 years unable to make it disappear. Let us be precise about what was actually detected. When JWST collected light from K218b's atmosphere during the 2023 transit, and when the team spread that light into its component wavelengths and read the absorption features, certain molecules declared themselves clearly. Carbon dioxide was there, methane was there. Both are consistent with a hydrogen-rich atmosphere of the type the Hycean model predicts, and neither is particularly surprising for a planet of this composition. But there was a third feature, fainter than the others, present in a wavelength range where several molecules leave overlapping marks, a signal that the team identified as most consistent with dimethyl sulfide, and potentially with a related compound called dimethyl disulfide. Both are sulfur-bearing organic molecules. Both are associated on Earth with biological activity, and neither had ever before been detected in the atmosphere of an exoplanet. The team published. They were careful. The paper used terms like potential biosignature and possible indicator. The word life did not appear as a conclusion. Madhusudan, in interviews that followed, chose his language with the precision of someone who understood exactly what was at stake in every syllable. The media did not make the same choice. Within hours of the paper's release, headlines around the world had translated potential indicators at 3 sigma statistical confidence into something far more absolute. Life found. Signs of alien life confirmed. Scientists detect organisms on distant planet. Researchers who had not yet read the paper received calls from journalists asking for their reaction to the discovery of extraterrestrial life, a discovery no one involved in the research had announced. This matters because the gap between what the science said and what the world heard shaped the debate that followed. Some of the sharpest criticism directed at the Cambridge team was not about their data. It was about whether they had handled the public communication of an extraordinary preliminary result responsibly. Madhusudan argued, reasonably, that he could not control how headlines translated qualified scientific language. The critics argued, also reasonably, that releasing results of this emotional magnitude into a media environment practically guaranteed that translation would occur. Set that dispute aside for a moment, because the science itself deserves full attention. Here is what 3 sigma means. When scientists report a detection at a given sigma level, they are describing a statistical relationship between the signal and the noise in their data. A 1 sigma result means the signal is just 1 standard deviation above the noise, barely distinguishable from random fluctuation. 3 sigma means the signal is 3 standard deviations above the noise, which corresponds to a probability of roughly 3 in 1,000 that the detection is a statistical accident rather than a real feature. In most branches of science, 3 sigma is convincing evidence. In chemistry, in medicine, in ecology, a 3 sigma result would be publishable and credible. But physics, and the subset of astronomy dealing with discoveries of fundamental importance, operates under a higher standard. The threshold for claiming a discovery is 5 sigma, which corresponds to a probability of less than 1 in 3.5 million that the signal is noise. 5 sigma is how the Higgs boson was confirmed. 5 sigma is how gravitational waves were announced. For something as consequential as a potential biosignature on another world, anything below 5 sigma is a signal to be investigated, not a result to be declared. The current K218b detection sits at approximately 3 sigma. That is not a small number, but it is not 5. Then came the reanalyses. Jake Taylor, working at Oxford, applied what he described as an unbiased retrieval analysis to the MIRI data, a method that makes no prior assumptions about which molecules to search for. Rather than starting with dimethyl sulfide as a candidate and asking how well it fits the spectrum, Taylor's approach fed the data to an algorithm and asked it to find the best-fitting model from scratch. His analysis returned a result consistent with a flat line. No statistically significant molecular features. The spectrum, by his method, was not clearly distinguishable from noise. A separate team at the University of Chicago took a different approach and combined the 2023 near-infrared dataset and the 2025 mid-infrared dataset into a joint analysis. If the signal is real, combining more data should strengthen it. Their analysis found no statistically significant detection of dimethyl sulfide when the 2 datasets were considered together. Madhusudan's team pushed back on both analyses. Their response was that Taylor's method used an oversimplified atmospheric model, one that could not reliably separate overlapping molecular features at JWST's spectral resolution. Their response to the Chicago analysis was that the joint weighting of the 2 datasets rested on assumptions that were not physically justified. The expanded model the Cambridge team developed in response incorporated 650 candidate molecules and continued to identify dimethyl sulfide as the most plausible explanation for the observed features. The critics noted that the model had changed substantially without any new data arriving. The team replied that more sophisticated modeling is a normal scientific response to methodological challenges. This exchange is not a scandal. It is not evidence of dishonesty or incompetence on either side. It is what contested frontier science looks like from the inside. Unglamorous, technical, fought over decimal places and modeling choices, conducted between researchers who respect each other's work and disagree about its interpretation. What it is not, as of early 2026, is resolved. The signal has been challenged. It has not been disproven. It has survived 2 independent instrument observations. It has not yet survived the statistical threshold that would make it a discovery. It sits in the uncomfortable territory between a hint and a fact, and it will remain there until more data arrives, or the reanalyses accumulate sufficient weight to collapse it. That is where the science stands. Now consider what it would mean if the signal is not coming from life at all. Oliver Shortall works in Cambridge, not in the sense that he works near Cambridge or at an institution affiliated with it. He works in Cambridge, at the same university as Niku Madhusudan, in a building you could reach from Madhusudan's office in the time it takes to finish a cup of coffee. The two most prominent opposing interpretations of what JWST has detected at K2-18b were developed within walking distance of each other by scientists who share seminar rooms and, almost certainly, occasional corridor conversations. Shortall is a geochemist, where Madhusudan thinks about planets from the atmosphere inward, starting with what the spectrum shows and reasoning toward what the interior might look like. Shortall thinks from the interior outward. He starts with the rock, with the chemistry of magma and mineral and the slow, violent processes that govern the deep interiors of massive planets. And when he applied that thinking to K2-18b, the picture he built looked nothing like a Hycean ocean world. It looked like a furnace. At K2-18b's mass, 8.6 times Earth, the interior of the planet generates enormous pressure and consequently enormous heat. Under those conditions, some planetary models do not converge on a liquid water ocean beneath the hydrogen atmosphere. They converge instead on a magma ocean, a global sea of molten rock, glowing at temperatures of thousands of degrees, churning through convection currents that cycle material from the deep interior to the base of the atmosphere and back down again over timescales of centuries or millennia. This is not a fringe interpretation. It is a physically motivated model drawn from the same planetary science that produced the Hycean hypothesis. And in some respects, its predictions fit the available data just as well. Here is where the magma model lands its most direct challenge to the biological reading of the signal. Ammonia, or rather, its absence. K2-18b's atmosphere contains notably less ammonia than you would expect from a planet of its composition if the chemical budget were dictated purely by equilibrium gas phase chemistry in a hydrogen-rich atmosphere. Madhusudan's team cited this ammonia deficit as evidence consistent with the Hycean model. Biology consumes nitrogen compounds, and a living ocean might plausibly draw ammonia down below its expected abundance. Shortall's models offer a different explanation entirely. In a magma ocean world, the molten rock at the base of the atmosphere is not chemically inert. It dissolves gases from the overlying atmosphere through a process of chemical absorption, and nitrogen compounds, including ammonia, dissolve into silicate melt with particular efficiency. The magma eats the ammonia, no biology required. The same observation that Madhusudan's team interprets as a potential biological signal is, in Shortall's framework, a straightforward consequence of magma-atmosphere chemistry. The methane and carbon dioxide that JWST detected, the atmospheric composition that the Hycean model identifies as consistent with a habitable world, are also produced in the magma model through high-temperature carbon chemistry at the boundary between the molten surface and the hydrogen sky above it. Volcanic outgassing from a magma ocean world generates both gases continuously. The atmospheric fingerprint that looks, from 124 light-years away, like the signature of a Hycean world also looks, within the uncertainties of current measurements, like the signature of a lifeless geological furnace. And the dimethyl sulfide. Laboratory experiments have confirmed that methane reacting with hydrogen sulfide, a volcanic gas released abundantly by molten rock, can produce sulfur-bearing organic compounds under high-temperature conditions. Dimethyl sulfide is among them. The yields measured in those experiments are currently 10 to 100 times lower than would be needed to explain the concentrations JWST appears to be detecting. But those experiments were conducted under Earth laboratory conditions, ambient temperature and pressure, far removed from the extreme environment of a magma ocean at the base of a massive hydrogen atmosphere. The actual production rates under K2-18b's specific conditions are unknown. They have not been measured. The gap between laboratory yield and observed concentration is real, but it has not been closed by direct experiment. There is a further challenge to the Heysian model that the magma ocean picture directly addresses: the albedo problem. For a Heysian ocean to maintain liquid water at its surface, the planet needs to reflect an extraordinary fraction of incoming starlight. Multiple research teams calculated in 2025 what that fraction would need to be and arrived at a number around 0.92, 92% reflectivity, a near-perfect mirror. For context, Earth's average albedo is around 0.3. Fresh snow reaches around 0.8 at best. No known planet achieves the reflectivity the Heysian surface temperature calculation requires, and current JWST observations of K2-18b show no evidence of the dense high-altitude cloud layers that would produce such extreme reflectivity. The atmosphere, as far as the data can currently show, is not topped by the brilliant, light-scattering clouds the liquid ocean model needs. In the magma ocean model, this is not a problem. A molten rock surface does not need to reflect 92% of incoming light. It absorbs it, radiates heat upward, drives the atmospheric chemistry, and produces, incidentally, a spectrum that a telescope 124 light-years away cannot easily distinguish from the spectrum of a Heysian world teeming with life. Apply Occam's razor to this situation, and the edge points uncomfortably away from the biological interpretation. The magma ocean explanation asks nothing extraordinary of the universe. It asks only that K2-18b behave like a planet of its mass, and composition is expected to behave. The Heysian model asks for liquid water at the right temperature, a specific atmospheric regime, the independent emergence of life, and the biological production of a specific molecule at concentrations 10,000 times those found in Earth's oceans. Simpler explanations, all else being equal, deserve the first hearing. But all else is not equal. And the thing that distinguishes this debate from a routine scientific dispute over a new planetary system is something the magma ocean model cannot easily account for: the prediction. The magma ocean model was developed in response to data that already existed. It looked at what JWST found and constructed a physically coherent explanation. That is legitimate science. It is exactly what competing models are supposed to do. But Madhusudan's Heysian framework did something different. It was published in 2021. The MIRI observation that produced the strongest version of the dimethyl sulfide signal did not occur until 2025. The prediction preceded the data by 4 years and named specifically the molecule, the concentration range, and the instrument capable of detecting it. In the evaluation of competing scientific claims, this asymmetry matters. A theory that anticipates an observation before it exists cannot have been fitted to that observation after the fact. The Heysian prediction could have been wrong. The data could have come back flat, or returned a different molecule entirely, or shown an atmosphere inconsistent with the model in ways that would have required it to be abandoned. It did not. The data matched the prediction. This does not settle the debate. The magma ocean model still fits the current data. The statistical threshold for discovery has not been crossed. But when you weigh the two frameworks against each other, the predictive success of the Heysian hypothesis is not a detail to absorb and move past. It is one of the most substantive arguments in its favor. And to properly evaluate it, to understand why the detection of dimethyl sulfide specifically carries the weight it does, and why its presence or absence matters so much more than the detection of, say, nitrogen or carbon monoxide, you need to understand what a biosignature actually is, not in the casual sense, in the rigorous sense. The intellectual foundation of biosignature science was laid in 1965 by James Lovelock, then working at NASA's Jet Propulsion Laboratory on the early theoretical groundwork for life detection strategies. Lovelock made a deceptively simple observation. A planet with life on it is not in chemical equilibrium. Life continuously produces and consumes gases, driving the atmosphere away from the state that chemistry alone would settle into if left undisturbed. The atmosphere of a living world is, in a technical sense, being held in disequilibrium by an ongoing biological pump, And that disequilibrium, Lovelock argued, is itself detectable. This idea sounds abstract until you apply it to Earth. Our atmosphere contains approximately 21% oxygen and trace amounts of methane. These two gases react with each other in the presence of sunlight. Oxygen and methane combine to form carbon dioxide and water, a reaction that proceeds continuously and that, in the absence of replenishment, would consume both gases within a few thousand years. A few thousand years is nothing on the timescale of planetary history. If Earth had no life, its atmospheric methane and oxygen would long since have reacted away and settled into a stable equilibrium. They have not settled. Both gases are present simultaneously, today, in quantities that chemistry alone cannot maintain. Something is continuously producing them faster than the reaction consumes them. That something is life. Photosynthesis produces oxygen. Methanogenic archaea in wetlands, ocean sediments, and the digestive systems of animals produce methane. The simultaneous presence of both gases is not a coincidence. It is the signature of a biological system working against thermodynamic equilibrium. This is the gold standard biosignature, not a single unusual molecule, but a chemically reactive pair maintained simultaneously against the chemistry that would otherwise destroy them. K218b has a fundamental limitation here. Methane is present in its atmosphere, but free oxygen is not, and in a hydrogen-dominated atmosphere, any oxygen that appeared would react with the surrounding hydrogen almost instantly and vanish. The gold standard ensemble is not available for this planet. The case for dimethyl sulfide therefore rests on a different kind of argument. Not thermodynamic disequilibrium, but source strength. The concentration is so high that known abiotic processes struggle to account for it. Eddie Schwieterman and his colleagues at the University of California, Riverside compiled the most comprehensive review of biosignature science available in 2018, a systematic examination of every remotely detectable sign of life that exoplanet observations might access. What that review made clear is how far the field had moved from the early assumption that any single molecule could function as a smoking gun. Every individual biosignature has an abiotic escape route. Oxygen can be produced by photolysis of water vapor on a world without life. Methane erupts from volcanoes. Phosphine forms in gas giant atmospheres through purely chemical means. Even dimethyl sulfide, as the Rosetta spacecraft discovered in the coma of Comet 67P, forms abiotically in the frozen chemistry of primitive solar system bodies. No single molecule is unambiguous proof of life. The response the field developed is biosignature ensembles, combinations of molecules that have no plausible shared abiotic source, whose simultaneous presence implies a common biological origin. Sarah Seeger at the Massachusetts Institute of Technology extended this thinking in a 2025 preprint, cataloging 15 candidate biosignature gases for exoplanet atmospheres, including methyl chloride, nitrous oxide, and several sulfur-bearing compounds. Some of these can be produced abiotically in isolation. Very few can be produced simultaneously by any known non-biological process. Dimethyl sulfide alone, at 3 sigma confidence, is a hint. Dimethyl sulfide confirmed at 5 sigma, accompanied by a detection of methyl chloride, a molecule with no known abiotic production pathway in planetary atmospheres, would be something categorically different. 2 independent molecular signals, each pointing toward biology, with no plausible geological mechanism capable of generating both at once. That second molecule has not yet been detected at K2-18b. Whether it is there waiting to be found, or absent because nothing is there to produce it, is a question the next round of observations may begin to answer. But before those observations can be understood in their full weight, there is a history that needs to be heard. Because this is not the first time humanity has stood at what appeared to be the threshold of a discovery like this one. And the previous times did not end well. On the 7th of August, 1996, President Bill Clinton walked to a podium in the Rose Garden at the White House and told the world that scientists might have found evidence of ancient life on Mars. He chose his words carefully. He said compelling evidence that might point to the possibility. He said if this discovery is confirmed, he said the findings would be the most stunning insight into our universe that science has ever uncovered. He was describing a meteorite, a piece of rock blasted off the Martian surface by an ancient asteroid impact, drifted through space for millions of years, entered Earth's atmosphere, and come to rest in the ice of the Allen Hills region of Antarctica, where it had been sitting, undetected, since approximately 13,000 years ago. It was recovered in 1984 and given the designation ALH 84001. David McKay and his colleagues at NASA had spent years studying it. What they reported in the journal Science was a convergence of 4 independent lines of evidence, each individually explainable without invoking biology, but all present in the same sample, pointing in the same direction. Microscopic structures resembling fossilized bacteria, far smaller than any known Earth bacterium, but structurally suggestive. Chemical compounds called polycyclic aromatic hydrocarbons, which are produced when organic molecules break down. Carbonate mineral globules of a type sometimes associated with biological activity on Earth. And crystals of magnetite with a morphology similar to those produced by a specific group of bacteria that use magnetic minerals for navigation, magnetotactic bacteria, organisms that build chains of tiny magnets inside their cells to orient themselves within Earth's magnetic field. Taken individually, each piece of evidence had an abiotic explanation. Taken together, McKay's team argued, they pointed toward the remnants of ancient Martian microbial life. The world wanted it to be true, and that wanting is precisely where the trouble began. Over the years that followed, the evidence was dismantled, piece by piece. The microscopic structures were too small, far smaller than any known living cell, and experiments demonstrated that similar structures could form through purely inorganic chemical processes with no biology involved. The polycyclic aromatic hydrocarbons were found throughout the meteorite, including in regions that had been exposed to Antarctic meltwater, carrying terrestrial contamination from Earth organisms. The carbonate globules could be explained by high-temperature chemical reactions requiring no biological involvement. The magnetite crystals, the most compelling element, the one that generated the most sustained scientific interest, remain debated even today. Some researchers still argue they show features consistent with biological production. The consensus, however, shifted away from the biological interpretation long ago. The discovery had not been made. The evidence, under scrutiny, had been insufficient, and the desire to confirm the result had moved faster than the evidence could support. That episode scarred astrobiology, not by discrediting it, but by embedding a deep institutional wariness into the field's culture. The 5 sigma threshold, the demand for multiple independent lines of evidence, the reflexive skepticism that now greets extraordinary claims before the data has even been examined. These are not arbitrary bureaucratic constraints. They are the direct institutional legacy of what happened when the world decided it had found Martian life 20 years too soon. Then came Venus. In September of 2020, Jane Greaves and her colleagues at Cardiff University announced the detection of phosphine in the atmosphere of Venus. The logic was compelling. On Earth, phosphine, a molecule consisting of 1 phosphorus atom bonded to 3 hydrogen atoms, is produced in only 2 contexts: by industrial chemical processes and by anaerobic bacteria living in oxygen-free environments. No natural abiotic process in a planetary atmosphere should generate significant quantities of it. If phosphine was present in Venus's clouds, something was making it. And the most parsimonious something was life. Microbial organisms floating in the Venusian atmosphere at altitudes where temperatures and pressures are, by planetary standards, relatively mild. The announcement was enormous. Coverage was immediate, breathless, and almost universally framed as evidence of life on Venus. For several weeks, it seemed as though the question of life in the solar system might be answered at the planet next door. Then, the reanalysis began. Ignaz Snellen and his colleagues at Leiden Observatory were among the first to scrutinize the data independently. What they found was a calibration error in the data reduction pipeline that had artificially amplified the signal. The phosphine feature, when corrected, dropped from approximately 20 parts per billion to around 1 part per billion, a level potentially explained by ordinary atmospheric chemistry without any biology required. Multiple independent teams subsequently found no convincing evidence for phosphine at all. The spectral feature the Cardiff team had identified overlapped with absorption lines from sulfur dioxide, a gas Venus has in known abundance. The signal had almost certainly been misidentified. The detection collapsed. Not because the Cardiff team had acted in bad faith, they had not, but because detecting molecules at the limits of instrument sensitivity, in atmospheres that are chemically complex and poorly characterized, using spectral features that overlap with other compounds, is a problem that is genuinely hard. False positives are not a sign of incompetence. They are a predictable consequence of operating at the frontier. Laura Kreidberg, an exoplanet atmospheric scientist at the Max Planck Institute for Astronomy, observed of the K2-18b situation that she had seen this movie before. She was not dismissing the detection. She was naming the pattern, the one that runs from ALH 84001 through the Venus phosphine affair, and now to the dimethyl sulfide signal, and asking the question that the history demands be asked before conclusions are drawn. What makes K218b different from these precedents is real, and it deserves to be stated plainly. The phosphine detection rested on a single instrument, a single observation, and a spectral feature with a direct alternative explanation. K2-18b's dimethyl sulfide signal has been returned by two independent instruments operating at zero wavelength overlap. It was predicted by theory before it was observed, and it has survived months of active attempts by the detecting team to disprove it. It has not collapsed, it has been challenged. Those are not the same thing, but the history earns its telling regardless, because it explains the culture of caution that surrounds this detection, and because that caution is not obstruction. It is the field's hard-won immune response to its own previous errors. With the history in place, the question that follows is a precise one. What specific evidence would move the K2-18b debate from contested signal to resolved science? The current ambiguity exists because both the Heysean biological model and the magma ocean abiotic model fit the available data within its measurement uncertainties. To break that tie, you need an observation that one model predicts and the other does not. And the molecule most capable of providing that is one the telescope has not yet confirmed: methyl chloride. On Earth, methyl chloride is produced by marine organisms and terrestrial vegetation through enzyme-mediated halogenation reactions, biological processes that attach chlorine atoms to simple carbon molecules. No known abiotic process in a planetary atmosphere produces it at concentrations comparable to what biology generates. Its spectral features fall within a wavelength range accessible to JWST. And critically, it shares no plausible abiotic production pathway with dimethyl sulfide. The two molecules are chemically distinct, biologically connected, and geologically unrelated. A detection of both simultaneously, each at statistically significant confidence, would represent two independent biological signals with no common geological explanation. That is a different category of evidence from a single molecule at 3 sigma. There is also the matter of disambiguating the current signal. Dimethyl sulfide and dimethyl disulfide, a related sulfur-bearing compound, have overlapping spectral features at the wavelengths JWST has so far examined. Distinguishing between them requires longer wavelength mid-infrared data, beyond 12 microns, where their absorption features diverge. Knowing which molecule is dominant matters for the interpretation, because their production mechanisms differ and each constrains the chemical environment in different ways. Ethane is another molecule that carries information precisely through its absence. In Earth's atmosphere, ethane appears alongside dimethyl sulfide as part of the biological sulfur cycle. It has not been detected in K2-18b's atmosphere. That absence is not necessarily significant. the detection sensitivity may simply be insufficient. But if future observations confirm it is genuinely not present, that places a constraint on any biological model that needs to be accounted for. The ammonia question remains unresolved in a way that cuts both ways. Both the Heysian model and the magma ocean model offer explanations for its deficit. A more precise upper limit on ammonia abundance, achievable with higher signal-to-noise observations, could begin to distinguish between biological consumption and magma dissolution as the responsible mechanism. And then there is the surface itself. The thermal emission spectrum of K218b, the infrared radiation emitted by the planet rather than the starlight transmitted through its atmosphere, carries information about surface temperature. A magma ocean glows at thousands of degrees. A liquid water ocean does not. In principle, a precise thermal emission measurement would resolve the question of what lies beneath the hydrogen sky more directly than any atmospheric molecule detection. That measurement has not yet been achieved, but it sits within the theoretical reach of extended JWST observations and is almost certainly within the planning horizon of the teams involved. The science knows what it needs. The instruments exist or are being built. The planet transits every 33 days. The answer is not waiting for a technological breakthrough. It is waiting for telescope time and for the data that time will eventually produce. What that data finds, and what it means either way, will be explored in the final movement of this story. But first, the human dimension of this debate deserves its full accounting, because the two scientists at the center of it are not abstractions. They are people. And the story of how they came to be on opposite sides of the most important question in modern astronomy, working 40 meters apart in the same city, is one that illuminates something important about how science works at its most intense. To understand why two rigorous teams running the same data through different methods can arrive at fundamentally different answers, you need to understand what atmospheric retrieval actually involves, because the word retrieval suggests something more straightforward than it is. When JWST collects light from K218b's atmosphere, what it records is a spectrum, a graph of how much light was absorbed at each wavelength across the range the instrument covers. That graph is real. It is data, but reading a chemical composition from it is not like reading words from a page. It is an inversion problem. You are working backwards from the observed effect to the cause that produced it, and the path from effect to cause is not unique. Many different atmospheric compositions can produce spectra that look similar, especially at the spectral resolution JWST achieves for a planet at this distance. Atmospheric retrieval is the set of mathematical techniques used to navigate this problem. The basic approach, in the form called Bayesian retrieval, works like this. You begin with a model atmosphere, a set of assumed parameters including temperature at different altitudes, cloud properties, and the abundances of various molecules. You run that model atmosphere through a forward calculation to generate a predicted spectrum. You compare the predicted spectrum to the observed one. Then you adjust the parameters, run again, compare again, and repeat this process many thousands of times, each iteration refining the parameter values toward those that best reproduce the data. The result is not a single answer, but a probability distribution, a statement about which combinations of atmospheric parameters are more or less consistent with what was observed. The difficulty lies in how many parameters you allow to vary. Every free parameter in the model is a degree of freedom, another dimension along which the model can adjust itself to fit the data. A model with many free parameters is flexible. It can fit a wide range of spectra. But that flexibility is a liability as much as an asset, because a sufficiently flexible model can fit noise as convincingly as it fits signal. This is overfitting. When the model learns the random fluctuations in the data as if they were real features, producing a confident-looking result that reflects the noise rather than the atmosphere. Madhusudan's team used a model that allowed the abundances of hundreds of molecules to vary freely, a comprehensive approach designed to explore a large chemical parameter space without prejudging which molecules might be present. Jake Taylor's approach at Oxford was different in philosophy. His method made no prior assumptions about which molecules to search for, instead letting the data itself drive the solution with minimal model complexity. When applied to the MIRI data, his approach returned a result consistent with a flat line, no significant molecular features. Both choices are defensible. That is the uncomfortable truth at the center of the methodological dispute. Madhusudan's team argues that a simpler model cannot reliably disentangle overlapping molecular features at JWST's spectral resolution, that the complexity of the atmospheric chemistry requires the flexibility they built in. Taylor's position is that a more complex model is more susceptible to finding signals in noise, particularly when the model has been constructed with a specific molecule in mind as the leading candidate. Neither team is obviously wrong. They made different choices about how to handle a genuinely hard problem, and those choices led to different answers. The resolution will not come from argument. It will come from more data, more transits, more photons, higher signal-to-noise, until the spectrum is constrained well enough that all reasonable retrieval approaches converge on the same answer. Laura Kreidberg at the Max Planck Institute for Astronomy has spent years developing one of the most widely used retrieval frameworks in exoplanet atmospheric science, a code called Petit-Rad-Trans. Her caution about the K218b detection is not the caution of someone unfamiliar with the technique. It is the caution of someone who understands exactly where the technique's limits lie, and who has seen, in her own work and across the field, how easily those limits can mislead. Her observation that she had seen this pattern before was not a dismissal of the signal. It was a statement about the structure of the problem: biosignature detection at the boundary of instrument sensitivity, using spectral features with overlapping alternative explanations in an atmosphere that is poorly constrained. This is where the history of false positives was made. The vigilance she brings to it is the appropriate response to that history. The dispute over retrieval methodology is, in one sense, a technical argument about mathematical choices. In another sense, it is the entire substance of the debate, because until the signal is strong enough that no reasonable method can return a flat line, the question of what JWST has actually seen at K2-18b cannot be answered with confidence. That is where the science stands, and it is enough to know. Now suppose, for the duration of what follows, that the signal is real, not confirmed. That word belongs to 5 sigma and a convergence of methods, but real. Suppose something is alive in the ocean of K2-18b, producing dimethyl sulfide in the quantities the detection implies. What does that life actually need to exist? What does its day, if a tidally locked world can be said to have a day, actually look like from the inside? Start with the most fundamental constraint. There is no free oxygen in K2-18b's atmosphere. None. In a hydrogen-dominated sky, any oxygen would react with the surrounding hydrogen almost immediately and disappear. This means that every metabolic pathway available to organisms on K2-18b is anaerobic, operating without oxygen, without the electron acceptor that powers virtually every complex organism on Earth, including every animal that has ever existed. This sounds like a limitation. It is not, in biological terms, an unusual one. For the first roughly 2 billion years of life on Earth, the atmosphere contained almost no free oxygen. The organisms that dominated our planet during that entire period were anaerobic. They were not primitive in the sense of being simple or fragile. They were exquisitely adapted to their environment, diverse, metabolically sophisticated, and successful enough to persist today in vast quantities in every oxygen-depleted environment on Earth, from deep-sea sediments to subsurface rock to the intestinal tracts of every animal alive. Anaerobic life is not a last resort, it is the default. The most plausible candidate organisms for K2-18b, given what the atmosphere appears to contain, are methanogens. These are archaea, single-celled organisms belonging to one of the 3 fundamental domains of life, alongside bacteria and the eukaryotes that include every plant, fungus, and animal. Methanogens use hydrogen gas as an energy source, combining it with carbon dioxide to produce methane and water. They do not require oxygen. They do not require light. They need only a supply of hydrogen and carbon dioxide, both of which K218b's atmosphere provides in abundance. The methane detected in K218b's atmosphere is consistent with methanogenic activity. So is the carbon dioxide. Methanogens are among the most ancient organisms on Earth, found in environments ranging from deep ocean hydrothermal vents to Antarctic subglacial lakes, from the cores of ancient permafrost to hot springs. They are believed to be among the earliest metabolic strategies to emerge after the origin of life. Organisms that may have been running their hydrogen to methane chemistry for close to 4 billion years, but methanogens do not produce dimethyl sulfide. That molecule requires sulfur chemistry, a different metabolic pathway, a different class of organism. On Earth, the biological sulfur cycle involves multiple distinct microbial lineages, organisms that reduce sulfate, organisms that oxidize sulfide, and phytoplankton that produce dimethyl sulfonionpropionate, the precursor compound whose breakdown releases dimethyl sulfide. The DMS signal at K2-18b, if biological, implies either a single organism capable of both hydrogen and sulfur metabolism, something with no close Earth analog, or an ecosystem, a community of metabolically distinct organisms, each exploiting a different chemical gradient, their combined atmospheric exhaust producing the signal JWST detects. An ecosystem, not one organism, many, interacting, competing, cycling nutrients through the ocean across geological time. The scale of biological activity, implied by the detected concentration, 10,000 times Earth's marine atmospheric background, is in itself extraordinary. On Earth, the ocean's entire phytoplankton population produces roughly 100 million tons of dimethyl sulfide per year. The implied production at K2-18b, even accounting for the slower photolytic destruction in a hydrogen atmosphere, requires biological fluxes that strain imagination. Whatever is producing this signal, if biology is the source, is not a trace population clinging to the edge of habitability. It is a biosphere. There is one more consideration worth holding, because it touches something the atmospheric signal cannot address. Deep below the photic zone, beyond the reach of even the red-orange light of K2-18 filtering down through hundreds of meters of pressurized ocean, the planet generates heat from its own interior. A world this massive, with a rocky core under enormous compression, almost certainly releases geothermal energy upward through the water column. And where geothermal heat meets cold water, where reduced chemical compounds mix with oxidized ones in the dark, on Earth, that is where hydrothermal vent communities live. Entire ecosystems that have never needed the sun. Tube worms and chemosynthetic bacteria, powered not by starlight, but by the chemistry of the planet beneath them. If K2-18b has an ocean floor, and the Heysian model proposes one, and if that floor is geologically active, which a planet of this mass and internal heat budget almost certainly is, then the deep ocean of K2-18b could harbor life that JWST will never see. Life that leaves no atmospheric trace. Life that exists in permanent darkness under pressure that would destroy any human engineering, indifferent to the telescope pointed at its world from across the galaxy. The signal, if real, captures only the surface. Whatever is generating the dimethyl sulfide, it is the fraction of the biology that lives close enough to the ocean's surface for a volatile molecule to escape upward through kilometers of water and into the hydrogen sky above. What lives deeper is, for now, beyond asking. There is something worth pausing on before the story moves forward. The two most prominent competing interpretations of what JWST has detected at K2-18b, the Heysian biological model and the magma ocean abiotic model, were not developed by scientists at rival institutions in different countries, working in isolation, discovering their disagreement when the papers crossed paths in a journal. They were developed by scientists who work in the same city, at the same university, in buildings separated by a few minutes on foot. Niku Madhusudan and Oliver Shortall are both at Cambridge. They share a university. They share seminar rooms. They have almost certainly discussed this disagreement face to face. This is not incidental detail. It says something important about how science works when the stakes are genuinely high. Madhusudan came to this question from theoretical physics. He moved into atmospheric astrophysics and spent years building the computational frameworks that allow spectroscopic data to be translated into planetary chemistry. The models that stand between raw telescope data and a statement about what an atmosphere actually contains. The 2021 Hycean paper was the culmination of sustained theoretical work on a class of planet the field had largely dismissed, an argument that the dismissal was premature, and a prediction specific enough to be tested within a foreseeable observational timeline. When JWST returned data consistent with that prediction, Madhusudan described the experience as surreal. A scientist who had spent years constructing a mathematical framework suddenly confronted with an observation that matched it. The gap between building a theory and having the universe answer, it is not something academic training prepares you for. His team spent the months before publication not celebrating, but attempting to disprove what they had found, testing every calibration assumption, building every alternative model, looking for the flaw that would let them set the result aside. They could not find it. That discipline is the thing to hold. Madhusudan has been precise in every public statement since. Potential biosignature, possible indicators. He has not said life detected. He has said what the evidence supports, and not one word more. That the media translated qualified language into something far more absolute was not a failure of his communication. It was a structural feature of how extraordinary preliminary results enter a world that wants them to be definitive. A world that has been waiting for this answer for as long as anyone can remember, and that finds it very difficult to sit with a hypothesis that is neither confirmed nor ruled out. Some senior scientists were sharply critical of how the 2025 results were released, not of the science, but of the timing and the surrounding context. The concern that releasing results of this emotional magnitude before the statistical case was complete would create a media environment almost impossible to walk back if the signal collapsed. Christopher Glein at the Southwest Research Institute stated plainly that without something unambiguous, the detection cannot be considered a smoking gun. His words were not a dismissal of the work. They were the application of exactly the standard that the history of astrobiology demands be maintained. The critics are not wrong to demand more. Madhusudan is not wrong to report what his instruments found. This tension is not a dysfunction. It is the scientific process operating under conditions of extraordinary public interest, and it will be resolved not by who makes the more persuasive argument, but by what the next set of observations actually returns. There is a structural problem here that goes beyond any individual scientist's choices, and it deserves naming. When results this emotionally loaded enter the public domain at 3 sigma confidence, before the discovery threshold has been crossed, before the competing models have been ruled out, before the methodological disputes have been resolved, they become almost impossible to hold in their correct frame. The public communication of science works well for clean stories with clear outcomes. It works poorly for the intermediate state that serious science actually occupies most of the time. A state of genuine uncertainty, where the data points in a direction but cannot yet be followed all the way to its conclusion. The K218b story is a long way from its conclusion. Holding that honestly, without either dismissing the signal or overstating it, is the discipline the moment requires. From the scientists, from the journalists, and from everyone who has been following it. Shortall's approach comes from a fundamentally different direction. He thinks about rocks, about the chemistry of melting and crystallization, about what happens when a planet's interior generates enough heat and pressure to maintain a global sea of molten silicate, about which gases escape from magma and which dissolve back into it. When his group applied that thinking to K218b and asked what the interior of a world at this mass most likely looks like from first principles, the answer their models produced was not a warm hydrogen ocean. It was a geological furnace, and one whose atmospheric chemistry was, within the uncertainties of current measurements, uncomfortably similar to what JWST observed. Shortall has been equally careful not to overclaim. He does not argue that K218b is a magma world. He argues that the current data is consistent with a magma world, just as it is consistent with a Hycean world, and that until observations capable of distinguishing between the two are made, intellectual honesty requires holding both possibilities open with equal seriousness. That is the honest position. Both scientists hold it. They disagree about which explanation is more physically plausible given what is currently known, and that disagreement, conducted between rigorous researchers working within the same institution, is producing better science than agreement ever would. Every challenge from Shortall's group has sharpened Madhusudan's team's modeling. Every methodological objection from Taylor and the Chicago group has pushed the field toward more robust retrieval frameworks. The controversy is not impeding the search for the answer. It is the search for the answer, working as it should. Now consider the clock. K218b transits its star every 33 days. That is the fundamental rhythm governing when additional data can arrive. Not every transit is observable. The geometry between the planet's orbit, its star, and JWST's position at the second Lagrange point means that only certain transit windows fall within a viable observing configuration for the telescope. But several windows per year do align, and each one is an opportunity to add photons to the dataset, to raise the signal-to-noise ratio, and to push the statistical confidence in either direction. The current detection sits at approximately 3 sigma from 2 transit observations. The working estimate from the teams involved is that 2 to 3 additional transit observations, analyzed together with the existing data, would either push the confidence above 5 sigma, the discovery threshold, or reveal that the signal weakens as more data accumulates, suggesting it was statistical noise rather than a real atmospheric feature. Either outcome is a resolution, neither is a failure. Both the Cambridge detection team and independent groups have submitted proposals for additional JWST observation time targeting K2-18b transits. The review process by which the Space Telescope Science Institute allocates that time is highly competitive. JWST is the most oversubscribed scientific instrument ever built, with proposals from thousands of research groups across dozens of countries competing for a finite number of observing hours each year. Whether the additional K2-18b observations are approved, and when those observations are scheduled, determines the timeline for crossing the 5 sigma threshold. But there is also the real possibility that data already exists. The gap between a JWST transit observation and a published result is not days, it is months. Raw data must be processed through careful pipeline reduction. Instrumental systematics must be identified and corrected. Atmospheric models must be run, refined, and compared. Papers must be written, submitted to journals, reviewed by independent experts, revised, and cleared for release. If additional K2-18b transit observations were collected in late 2025 or early 2026, the analysis of that data may already be underway. In Cambridge, in Oxford, in Chicago, in Zurich, wherever the various teams have access to the raw data files. The answer may already be in a folder on a university server, a number in a spreadsheet, a confidence interval that either crosses 5 sigma or stubbornly refuses to. It exists or it does not, independently of whether anyone has published it yet. The universe is not waiting for the paper. The next round of observations will also need to address the molecule-specific targets that the current data leaves unresolved. Longer wavelength mid-infrared coverage to separate the dimethyl sulfide signal from the overlapping dimethyl disulfide features. A search for methyl chloride in the wavelength ranges JWST can access. More precise constraints on the ammonia upper limit. Higher signal-to-noise on every existing molecular feature to reduce the retrieval ambiguity that currently allows 2 legitimate methods to return different answers from the same spectrum. And if any of those observations return a positive result for methyl chloride, a second biologically associated molecule with no known shared abiotic production pathway, the nature of the debate changes entirely. Two molecules, chemically independent, each pointing toward biology, with no plausible geological mechanism capable of generating both simultaneously. That is not a smoking gun in the absolute sense. Science does not deal in absolutes, but it is the kind of converging evidence the field identified after the lessons of ALH 84001 and the Venus phosphine as the minimum required before the word discovery can honestly be used. The planet transits again soon. The data flows when it does. At the speed of light, across 124 light-years, arriving at a mirror 1 million miles from Earth, absorbed by detectors cooled to within 40 degrees of absolute zero, converted into numbers, transmitted to servers, and processed by scientists who have spent years building the tools to read what it contains. The answer is already on its way. What that answer means for the universe, for life, for the oldest question our species has ever asked, is where the story goes now. JWST will not be the last instrument to look at K218b. And K218b will not be the last world whose atmosphere humanity examines for the chemistry of life. The telescope that found this signal is the beginning of an observational era, not its culmination. And the instruments being built right now, on mountaintops, in engineering facilities, in design offices where proposals are still being drafted, will transform what is possible within a decade. The most consequential of these, for exoplanet atmospheric science in the near term, is the extremely large telescope. It is under construction at Cerro Armazones in the Atacama Desert of Chile, at an altitude of over 3,000 meters, where the atmosphere is thin and stable and the nights are among the clearest on Earth. Its primary mirror is 39 meters in diameter, composed of 798 individual hexagonal segments, each one polished to sub-nanometer precision and together forming a light-collecting surface roughly 6 times the area of JWST's. First light is expected around 2030, operated by the European Southern Observatory. For molecular identification in exoplanet atmospheres, the extremely large telescope offers something JWST cannot fully provide: spectral resolution high enough to separate individual molecular absorption lines that JWST blurs into broad overlapping features. The ambiguity that currently allows 2 retrieval methods to return different answers from the same K2-18b spectrum exists partly because the spectral resolution is insufficient to cleanly resolve which molecules are contributing to which absorption features. A 39-meter mirror with high-resolution spectrographs changes that calculation for the targets it can reach. K2-18b itself is at the edge of what the extremely large telescope can usefully characterize. The system is optimized for smaller, closer planets, orbiting fainter, nearby stars, and 124 light-years is a significant distance even for this instrument. But the telescope's greatest contribution to the K2-18b question may be indirect. The retrieval problem that currently sits at the heart of the K2-18b dispute, the fact that different modeling choices return different answers from the same spectrum, is partly a consequence of spectral resolution. JWST sees broad molecular features. High-resolution spectroscopy resolves individual absorption lines within those features, each one a precise wavelength fingerprint belonging to a specific molecule and no other. At that level of detail, the ambiguity that currently allows 2 legitimate retrieval approaches to diverge narrows sharply. Methods developed and validated on nearby, well-characterized targets using the extremely large telescope will feed directly back into how the community interprets JWST data on systems like K2-18b, tightening the models, closing the parameter space, and reducing the range of atmospheric compositions consistent with what the spectrum shows. By characterizing nearby rocky planets around red dwarf stars, worlds within 40 light-years, in enough spectral detail to begin searching for biosignature ensembles rather than single molecules, the extremely large telescope will establish the broader context in which K2-18b's sub-Neptune signal sits. If those searches return positive results, K218b becomes part of a larger pattern. If they return nothing, the context shifts, and the interpretation of K218b's signal must shift with it. The targets that will define that nearby search are already known. The TRAPPIST-1 system, discovered by Michael Gillen and his colleagues at the University of Liège, contains 7 rocky planets orbiting a red dwarf approximately 40 light-years from Earth. 2 of them, TRAPPIST-1e and TRAPPIST-1f, sit within the habitable zone and have masses and radii consistent with rocky compositions. They are among the most promising nearby targets for atmospheric characterization of potentially habitable rocky worlds. The extremely large telescope will be able to reach them in ways no current instrument can. Proxima Centauri b, orbiting the nearest star to our Sun at just over 4 light-years, is another. Whether it retains an atmosphere at all, given Proxima Centauri's activity as a red dwarf, remains genuinely uncertain. But its proximity makes it the most accessible, potentially habitable exoplanet candidate by a substantial margin, and the extremely large telescope will examine it with a thoroughness that JWST, despite its power, cannot match for a planet detected by radial velocity rather than transit. Further out on the timeline, there is a telescope that does not yet exist, but whose design is already being worked through in detail: the Habitable Worlds Observatory. This is NASA's proposed flagship space telescope for the following generation of exoplanet science, a large aperture instrument designed from the ground up for a single primary purpose. Not galaxy formation, not the early universe, the direct imaging of Earth-like planets around Sun-like stars, and the characterization of their atmospheres for biosignatures. Unlike JWST's transmission spectroscopy, which works only when a planet transits its star and requires a specific orbital geometry, the Habitable Worlds Observatory would use a coronagraph or a starshade, a precisely shaped occulting disk deployed in space to block the overwhelming glare of the host star, to image the planet directly. The reflected light of an Earth-like world around a Sun-like star, separated from the stellar glare, carrying the full atmospheric spectrum. That spectrum, analyzed for the oxygen-methane ensemble and the broader range of biosignature combinations, would be the most direct possible search for life beyond Earth. Launch is planned for some time in the 2040s. By then, K218b will almost certainly be resolved. The planet is a JWST question. It does not require a mission to be designed or a technology to be invented. It requires observing time on an instrument already in operation, pointed at a planet already identified, analyzing a signal already detected. The answer to whether K218b harbors life belongs to this decade, to the scientists currently running the analyses, filing the proposals, waiting for the transit windows to open. The Habitable Worlds Observatory will inherit a field that has already answered the K218b question and is ready to ask the next one. It will be built and operated by the generation of scientists who are now, perhaps, completing their doctoral work, or sitting in lecture halls hearing about K218b for the first time and deciding that this is the question they want to spend their career on. The generational structure of the search is real. What JWST can answer, it will answer. What the extremely large telescope can answer, it will answer in the 2030s. What the Habitable Worlds Observatory can answer will come in the 2040s and beyond. The search does not have an endpoint. It has a horizon that retreats as you approach it, always revealing more territory. But the horizon moves. What was beyond reach a decade ago is being measured now. What is beyond reach now will be reached. Now suppose the signal at K2-18b holds. Suppose the additional observations arrive, and the confidence climbs through 4 sigma, and then 5. Suppose methyl chloride is detected alongside dimethyl sulfide. Suppose the magma ocean models are ruled out by thermal emission data showing a surface temperature inconsistent with molten rock. Suppose a press conference is scheduled and the world prepares to hear what the scientists have found. What happens next? Not to the science, to us. In 1950, The physicist Enrico Fermi was having lunch with colleagues at Los Alamos and posed a question that has occupied science and philosophy ever since. If the universe is so vast, if there are so many stars, if so many of those stars have planets, if the conditions for life appear to be achievable, why have we not found any evidence of another civilization? Why is the galaxy not demonstrably full of signals, probes, artifacts, the accumulated traces of minds that have had billions of years to make themselves known? The question has no widely accepted answer. Dozens of proposed solutions exist, and none is fully satisfying. Perhaps life is genuinely rare. The emergence of even the simplest, self-replicating chemistry, so improbable that in a galaxy of 400 billion stars, it has happened only once, here. Perhaps life is common, but intelligence is vanishingly rare. The path from microbe to complex cognition, so long and unlikely that almost nothing completes it. Perhaps civilizations destroy themselves before they can communicate across interstellar distances. Perhaps something else, something we have not yet imagined, explains the silence. A confirmed detection of microbial life at K218b would transform this calculation instantly and irreversibly. If life arose independently on K218b, a sub-Neptune in the habitable zone of a red dwarf in a star system chosen essentially at random among the first targets of exoplanet atmosphere characterization, the statistical implication is stark. Two independent origins of life in a galaxy with 400 billion stars suggests that life is not a singular miracle requiring extraordinary coincidence. It suggests that life is something the universe does, a process that emerges wherever the conditions are sufficiently permissive and maintained for long enough. Not an exception, a tendency. And if life is common, the Fermi paradox sharpens into something that is no longer merely puzzling. It becomes genuinely alarming. If life is common, and if intelligence is possible, even rarely, even once in a billion biospheres, then the silence of the cosmos is not the silence of an empty universe. It is the silence of a universe where something prevents civilizations from persisting long enough to make themselves heard across interstellar distances. That filter, whatever it is, either lies behind us in the improbability of abiogenesis, or the emergence of eukaryotic cells, or the evolution of complex animal life, all of which we have already navigated, or it lies ahead. If it lies ahead, it waits for every civilization that reaches the level of technological development our own has now achieved. Nick Bostrom at Oxford, who formalized much of the philosophical framework around this question, observed that a universe teeming with microbial life but empty of civilizations is among the most disturbing possible configurations. The absence of other minds in the cosmos has until now been compatible with the hypothesis that the path from chemistry to civilization is simply long and rare. A confirmed second origin of life removes one of the filters. The remaining ones have to do more work. There is also the question of what confirmation would do to our understanding of ourselves, not through the lens of the Fermi paradox, but through the simpler, older lens of our place in things. The history of human cosmology is a history of successive demotions. The Earth orbits the Sun, not the reverse. The Sun is one of 400 billion stars in the Milky Way. The Milky Way is one of an estimated 2 trillion galaxies in the observable universe. Each demotion was philosophically disorienting in its time, resisted by those for whom the older picture provided meaning, eventually absorbed into the new understanding that replaced it. The confirmation of extraterrestrial life would be the next step in that sequence, the last claim to cosmic uniqueness that Earth retains. The claim that life is what makes our planet singular, retired in a single announcement. Surveys conducted in recent years, including work by researchers at the University of Arizona and the SETI Institute, have found that most people, when asked directly, expect to respond to such a confirmation with curiosity and awe rather than crisis or despair. That may be right. Or it may reflect the difficulty of genuinely imagining an experience that has no precedent. predicting your emotional response to something that has never happened to any human being in the history of the species. We do not know how we would feel, because we have never been here before. Hold that thought. It is real, and it is worth carrying into whatever comes next in your own thinking about this. But set it aside for a moment, because there is something else the confirmation would do. Something quieter and perhaps more fundamental than the recalculation of the Fermi paradox. Michael Wong at Carnegie Science, reflecting on the state of the field in April of 2025, said simply that it would be a remarkable thing to be alive at this moment. He was right, though the remark deserves expansion. Every human being who has ever looked at the night sky and felt the pull of the question, whether in a cave or a field or a temple or a laboratory, was asking without the tools to answer. The philosophers who proposed, 2,500 years ago, that other worlds must exist, were reasoning from first principles with no way to verify the conclusion. The astronomers who built the first telescopes and turned them on the sky were centuries away from the instruments capable of detecting a planet, let alone its atmosphere. The scientists who launched the first exoplanet surveys were a generation away from a telescope sensitive enough to read a molecular signal in the atmosphere of a habitable zone world. We are the first generation in the entire history of our species to have crossed that final threshold. The tools exist, the targets are identified, the observations are being made, the signal is in the data. It may be biological, it may not be, but the question is no longer philosophical, it is empirical. It is being answered in real time by instruments pointed at a specific star in a specific direction in a sky full of stars that each carry the same possibility. That is not a small thing to be alive for. The signal began 124 years ago. Not the detection, the light. The photons that JWST's mirror absorbed when it recorded K2-18b's transit left that star's atmosphere when the year was 1901. The Wright brothers had not yet flown. Einstein had not yet published. The word galaxy was not widely used to mean what it means now. The planet we are asking about was entirely unknown. The telescope that would one day read its chemistry did not exist even as a concept. Those photons crossed the distance between K2-18 and our solar system at the only speed the universe permits, entering JWST's instruments at the second Lagrange point, absorbed into gold-coated beryllium, converted to electrical signal, transmitted to Earth, processed, modeled, debated, and somewhere in the pattern of absorbed wavelengths they carried, somewhere in the particular arrangement of dark lines in a spectrum, is an answer to the question that no human generation before ours was equipped to ask with data. K2-18b is out there right now, the same world it was when the light you are living by left it. The hydrogen atmosphere churns in its ceaseless wind from dayside to nightside. The red star hangs motionless on the horizon of the Terminator, casting shadows that have not moved in 1 billion years. Whatever lies beneath, ocean or magma, water or fire, it presses up against the base of that sky with the patience of geology, indifferent to the debate it has ignited 124 light-years away. And somewhere in that atmosphere, a molecule that smells of the sea is either rising from something alive or forming from something ancient and geological and utterly without thought. We do not yet know which, but we are the first generation in the history of this planet to be close enough to the answer that we can feel its weight. The smell was always there. We just learned, finally, to look for its source.